Hello everyone, today we will be discussing machine translation, its concepts, techniques, and future directions. My name is Yashwant Yarasam and I am joined by Harshita Jangama. We are excited to take you through the evolution, its core concepts, and future of automated language translation. Here's what we will be covering today: an introduction to machine translation, its historical evolution, key approaches, core concepts, evolution metrics, challenges, applications, ethical concerns, and future directions. Let's get started. We will start discussing introduction to machine translation. Machine translation refers to automatical conversion of text or speech from one language to another using combinational methods. It plays a crucial role in breaking language barriers and enabling global communication across domains such as business, media, and academic. And the scope of it is text based and speech based. Historical evolution. Machine translation has evolved significantly over time. It started in 1950s with rule-based systems, then 1980s and 1990s saw the rise of statistical machine translation, followed by the dominance of neutral machine translation in mid 2010s with models like Google Neutral Machine Translation. Approaches to machine translation. There are three main approaches. The first one is rule-based machine translation. This method relies on predefined linguistic rules and dictionaries. While interpretable, it requires extensive manual work and struggles with unstructured text. Second one, statistical machine translation. This approach analyzes large amounts of bilingual text data to generate translations. Although effective, often lacks fluency because it treats words as independent units rather than considering entire sentences. Neural machine translation, the most advanced method using deep learning techniques to process entire sentences at a time or just at once. NMT models, especially transforms, generate more fluid and contextually accurate translations. Key components in machine translation systems: parallel corpora, aligned sentence pairs for training, alignment models, link words or phrases between source and target, language models, predicts word sequences in target language, and last decoder generates the final translation. Data preprocessing and machine translation. To train a machine translation model, text data must be clean and processed. First step is tokenization, splitting text into words, subwords, normalization, converting to lowercase, removing punctuation, and etc. Cleaning, removing a noisy or misaligned sentence pairs, handling rare words, using byte pair encoding to break words into subword units. Overview of neural machine translation. It's an end-to-end paradigm, which means single neural networks learns to map various sources to target sequences. Now let's look into encoder-decoder architecture. Encoder converts sentences into vectors, where decoder generates words in target language. Whereas attention mechanism helps the model focus on key parts of a sentence. Recurrent neural networks in machine translation uses recurrent neural networks like long short-term memory or gated recurrent units. The main challenges are vanishing gradients, poor long sequence handling. Badano attention improves long sequence translations. Pros and cons are: pros captures better context than SMT. Cons: slow training, struggles with very long sentences. Transformer architecture. Transformers are the most powerful neural machine translation models today. Their key innovations include self-attention mechanism. Every word in a sentence attends to every other word. Multi-head attention captures multiple relationships between words. Positional encoding ensures order is preserved without recurrence. These features make transformers the backbone of modern artificial intelligence translation tools. Attention mechanism. It allows models to focus on important words, improving translation quality. Alignment vectors determines how much focus should be on each source token. The main benefits of this is mitigates information bottleneck in fixed length vector representations and mainly improves handling of long sentences. Implementation includes weighted sum of encoder outputs for each decoder step. Performance evaluation metrics. Translation quality is assessed using various metrics. The first metric is bilingual evaluation under study. Measures n-gram overlap between machine and human translations. The second metric is metric for evaluation of translation with explicit ordering. Consider synonyms, stemming, and word order. Last but not least, translation edit rate. Calculates the number of edits required to correct the machine translation. Despite any of these automated metrics, human evaluation remains the gold standard. Challenges and limitations. Despite advancements, machine translation faces challenges such as data scarcity, low resource languages, lack large parallel corpora, ambiguity and context sensitivity. Words can have multiple meanings based on context. Low resource languages, limited training data makes it difficult to achieve high accuracy for less commonly spoken languages. Computational cost. Neural machine translation requires significant hardware sources, making it expensive to deploy at scale. Applications of machine translation and case study. Machine translation is used in real time translation tools like Google Translate and Microsoft Translator, and by many other companies too. E commerce platforms for product description translations, healthcare to translate medical records and prescriptions. Let's discuss a case study. Google Translate leverages large scale transformer models to support 100 plus languages. Despite its efficiency, it struggles with domain specific and idiomatic translations. Let's discuss advanced methods. Zero shot translation translates unseen language pairs without direct data. Multilingual neural machine translation. Single model translates into multiple languages. Main benefits are efficient, supports low resource languages too.
Hello everyone, I'm Harshita. Now we'll see the domain adaptation strategies. Domain adaptation that helps machine translation to improve accuracy when applied to specialized fields like medical, legal, or scientific text. The key techniques of it are fine tuning, transfer learning, and the active learning. Coming to the fine tuning, that trains a general neural machine translation model on a broad data and continuous training on the domain specific text. Whereas the transfer learning that uses knowledge from high resource domains to improve performance in a low resource domains. For example, training on an English German financial data to enhance English Dutch financial translation. And the active learning that selects data strategically for better performance. For example, prioritizing array word translations for review by human translators before retraining it. And this is the code snippet example. Here the machine translation requires all the parallel data sets. And here is the Python code as a code snippet. And the function load parallel data that loads the bilingual sentence pairs. And these are used for the supervised learning and translation models. And this part of the code sets up a transformer based machine translation model, and we can count on the key aspects of it like vocab size that counts the unique words in source and target languages, and the D mode, that's the dimensionality of word embeddings, and the number encoding layers. If we take 6, then that would be 6 layer transformer encoder decoder. And in the training loop, that trains the model on the batches of data over the multiple reports, and that uses validation loss to check the module accuracy, and the trained module that is used for the future translations. Now after the code, now we'll go into a case study a Google Neural Machine Translation. So before it was Neural Machine Translation, the Google Translator used phrase-based statistical MT, which was very accurate but failed in fluency. Then after we came into NMT that adopted RNN based NMT with an attention mechanism. And the current status is we are using transformer models for state of the art performance. So on architecture, we can say that from SMT transformed to RNN NMT, and the transformer NMT, the previous one, the present one, and the improvement of it is it can better handle the context and reduced word for word transcription errors, and the impact would be fluency and natural sounding translation, and it outperforms older methods in long sentence translations. Now we'll see the industry use and integrations of it. Machine translation is widely used in businesses and services. Popular APIs and services are Google Cloud Translation API, Microsoft Azure, and AWS Translation. And in the business integration for the customer support, e-commerce, and enterprise solutions. Customer supports that would be chatbots with instant translation of language, and in the e-commerce translating product description for global markets, and in the enterprise solution that communicates internally and also across the multinational teams. So now we'll discuss the ethical and societal considerations of why this machine translation is developed. So machine translation affects peoples and cultures in very significant ways. For example, bias in translation, like gender bias. Some languages, they lack gender neutral pronouns leading to misinterpretations. For example, he's a doctor. Incorrectly translated as male in some languages. And the cultural sensitivity, automatic translation sometimes fails in respecting cultural nuances, and the misinformation risks, incorrect translations can be harmful, and the privacy concerns of it, data from online transactions can be stored and analyzed, impact on lower resource languages, over reliance on major languages like English, French, Chinese may reduce the usage of the minority languages like Hindi. Now we'll see the future scope of the machine translation. It focuses on improving the accuracy, efficiency, and multimodal capabilities. Now, which it is like 98% to get on to the 100%, that would be the future scope. First one is multimodal translation. It integrates text, audio, and images all together. Like for example, translating a signboard image into another language using both the text recognition and the context understanding, and the context aware NMT. Beyond the sentence level translation, we are using like entire paragraphs for better context. And the interactive machine translation, users can correct translation in real time, the AI model, which is trend in the society. Now, low resource language support, transfer learning, and the unsupervised learning are helping expand translation capabilities. Example would be AI models again. Now we'll summarize all the key points. First one is the evolution from the rule-based to statistical, and the statistical currently the neural translation models, and the neural dominance or transformers dominate modern machine translation system, and in the evaluation metrics, TER and the human assessments, they measure quality. And the real world purposes, it is used in online transaction and the customer support, e-commerce, and the content localization as we previously discussed. And the challenges of it is bias, domain specific accuracy, real time performance. These are the factors which still need the improvement. And the future trends of this project is it focuses on the multi-modal, interactive, and the low resource language support. And here are all the listed references which we have taken for this project. which calculates all the previous methods, traditional methods, and the current machine translation methods, and the problems and the future scope of it. And this is all about the machine translation. Thank you for this opportunity.